this talk is called Programming Indie Games, A Decade of Mistakes. I'll get into what that means shortly. So, okay, let's do there. Okay, so this is me. So my name's Graham. I'm an engineering manager at SpryFox. I've been in the games industry since 2010. I've been writing game code since 2002 when I was in high school. I have a degree in computer science, direct media game development from WPI. I was a double major. I run the Boston Unity group with some folks, Chris and Elliot, who may be here, may not be. I've written for some Game AI Pro books, spoken at the Game AI Summit, and basically what I want to get across here is I've been doing this for a long time. And my experience in the industry is sort of split between like I know I do a lot of Unity stuff, and that's probably what I'm best known for in Boston. But my experience has been sort of 50-50 split between Unity and using and writing custom game engines. So the things I'm about to talk about are not necessarily Unity specific. They are certainly applicable to Unity for sure, but they're not by any means specific to Unity. So these are the games I worked on, the Field Runners games, Shadow Mortar, Alpha Bear 2. So Alpha Bear 2, I was the sort of principal engineer on that for a year and a half. It's the game I'm most proud of. Is the GDC Game Developers Choice Awards Best Mobile Game. Honorable mention. We lost to Florence, which was totally okay with me. That game is amazing. But yeah, I'm very proud of that. So I also worked on Seabirds, which was an indie bullet hell MMO. So that was a totally different experience. And then most recently, we launched a game called Cozy Grove, which is like Animal Crossing meets Don't Starve meets Night in the Woods. So that was a team of 22, and I was a manager of engineering team of 9 people on that project. It was 2 years, and it simul-shipped on lots of stuff. So 5 years of iPhones and iPads. There's like 30 different variants. 2 Apple TVs, 10 years of Mac variants, Windows, Xbox One, Switch, PS4, PS5. Cool. So now that I'm done patting myself in the back. So what does this talk about? So this talk is about sharing my wisdom and sort of opinions from working in the games industry. And it's a lot of stuff that I've learned the hard way. So a lot of this came from making lots of mistakes and sort of very dearly paying for them in many cases. And a lot of this is really not something that you learn in school. Even in game development programs, like it's stuff that you pick up from experience, and a lot of the times is actually contrary to a lot of things you learn in school as sort of like the best practices. So that's sort of the interesting part of it, and that's what I wanted to talk about today. So, okay, so a while back I was working on the Seabirds, the MMO, and I ran across. I was working on crafting, and we were trying to make some changes to crafting, and crafting ended up being implemented as reusing the quest system because it was just like a quest that had no requirements, and you just immediately turn it in and got the reward. And I got a little salty because it was, hard to work there, work in that context, and there were all these constraints, and I was breaking a bunch of things that weren't even related to what I was trying to do. So I wrote this tweet, and it weirdly went kind of viral. Like I didn't expect this at all. I was just sort of yelling into the void as one does on Twitter. But I think the reason why this gained so much traction is because it really hit a nerve, right? It's like this is a thing that we all kind of are thinking about in the back of our head, whether we realize it or not. And so, okay, so the tweet is, 99% of cases, it's better hard code your logic than to preemptively abstract something so it's reusable or generic. Writing reusable code takes 3 times longer, is very difficult to do well, and is inherently resistant to change and iteration. And then there's a few follow-ups, which I'll get into later. But the sort of idea here was that like I was running into this situation where it was really hard to change the thing that I wanted to change because of these tactics that were employed to make it to reuse something or to make a generic system to support different things in the code. So in general, like the reaction to this were sort of like this bell curve of between strongly disagree, disagree, agree, strongly agree. Most people were like, yeah, I kind of agree with you, or yeah, I kind of don't agree with you. There were some people who were like, oh my God, this. And then there were other people who were like, this fucking guy, like, get out of here. So it was pretty fun. It was really nice to hear a lot of different opinions and where people were coming from and stuff. So it's actually like a really, really interesting experience. Okay, so the first thing I want to talk about with regards to all of this is what it actually means to be an engineer, right? So in the broader context of just engineering, like life, right? Engineers, what do? They analyze problems. They objectively evaluate solutions to problems given constraints, and then they determine and implement the most appropriate solution to solve that problem, right? So forgive my I'm a car guy, so you have to forgive my analogy here, but this question, what are you optimizing for, right? So we have a picture of a Toyota Corolla and a top fuel drag car, which are two sort of different ends of the spectrum in cars. So just some context, if you're not into cars, Toyota is just what you think of a car to be, and a top fuel drag car is purpose-built race car, does quarter miles in 3 seconds, 0 to 300 miles an hour, and whatever. Like, so if you're working on the Toyota, your constraints are way different than if you're working on the drag car, right? I mean, that's pretty obvious. And so your solutions are going to be drastically different, right? So I think the most notable drastic difference, like obviously like the Toyota has like air conditioning and seats, but the most drastic difference is the reliability, right? Like a Toyota will go 100,000 miles easy, probably 400,000 miles. And these top fuel drag cars, they're blow the Toyota out of the water in every respect of like speed and performance. But after every race, they have to take apart the entire engine and rebuild it from scratch, because it's like it destroys the engine, right? Because they've optimized so much for this one thing that is the thing that matters, right? It doesn't matter that it's not reliable. It doesn't matter it doesn't have a CD player. It matters that it goes fast, because that's what they're trying to solve for. Okay, back to games. So what are we optimizing for with games, right? There's the obvious memory usage, CPU time, yada yada. There's also things like implementation time, right? How long does it take to write the code? How long does it take to change or maintain the code, right? How easy is that? How easy is it to add things like tooling for designers, right? How easy is it for other people to interact with the code who are not engineers? Another thing we could optimize for is reducing interdependencies between systems. So we could say, we're writing this code to exist with the minimum amount of requirements, right? So that would be useful if you're writing a library, right? Otherwise, you sort of have the NPM problem where you try to install one thing and it installs like the world, because it all depends on these things, which depend on these things, which depend on these things. So that could be a thing you're optimizing for, right? There are other things too, like networking models. You can have a specific networking model that you have to fit your solution into. So if you're working on like World of Warcraft, like you can't, do this category of problems because it has to fit within the networking model for World of Warcraft, right? Anyway, so there's a lot of constraints that we have to work within. And I think a thing that really illustrates this and will sort of is something that maybe you've experienced, is the difference between writing like game jam code and not game jam code, right? So game jam code is obviously much faster to get working, right? We only have 48 hours to make a game. You do everything you possibly can to get that game working within 48 hours. That's what a game jam is. And the reason you're able to do that is because you're consciously or subconsciously, you're optimizing specifically for implementation time, right? You're cutting away everything that is in the way between not having a thing and having a thing, right? You're just doing the minimum amount of work required to get the solution that you need. So that's a great example of implementing for or optimizing for implementation time. Cool. So engineers in studios, what is our role there? So I like to think of engineers as team force multipliers, right? So every game needs code, but we are also very heavily involved in the process of making the game, right? So we can do things like we can make tools, we can make systems that allow designers to do more than they would be able to do on their own, or artists, vice versa, or alternatively, we can also be a burden to the team, right? So we could be a multiplier that's less than 1, right? So what that would manifest as is like, there's all these things that the team wants to do, but we can't do it because of all these technical reasons. So when we're working as engineers in studios, we're really striving to be this force multiplier that's greater than 1, right? We're trying to enable the rest of our team to be awesome, right? And get out of the way as much as possible, right? So in that sense, being predictable and reliable with your work is the biggest asset you can bring to a team, right? Whether you can look at a problem and say, yes, we can solve that, and we can solve it well, and we can solve it correctly, or not. Like that's how you work well in a team as an engineer, right? So how do you sort of get to this, ideal of being a greater than 1 multiplier, right? So I think the first thing is you really have to know your platform. And I will use an awesome video to illustrate this. So this is a bunch of people who are not martial artists trying to use a real deal katana and cut through these straw mats, right? And you can see people are very various levels of success. That we'll eventually get to. I'll sort of fast forward a little bit. There's this guy who's he's the master, right? He's been doing this for a long time. He knows exactly what he's doing, and wham, right? Yeah. So what I'm trying to get across here is that it's not about the tool, right? So everybody in this video had the same sword, right? It's the same sword, it's the same mats, it's the same everything. It's how you use it and how you understand it and how you a lot of people were doing the same body motions he was, but they weren't doing it in just the right way, and they weren't understanding the subtlety of the angle, and they were understanding how you apply your force in the right way, and how you all of these details around what they're doing, but they were still using the industry standard gold whatever katana to try to do this, but they just didn't understand how to do it, right? And that comes down to knowing your tools and knowing your platform. So let me skip ahead here. Cool. So in terms of games, what this means is knowing stuff like CPU caches, data access speeds, memory layout, allocation strategies, paging, SIMD, threads, parallelism, file systems, DLLs, linking, OS nuances. It's a lot, right? It's a lot of stuff. Unfortunately, computers these days are really complicated, and the path from you writing a piece of code and it running on the machine is this huge stack of stuff that you have to kind of understand. There's really no way around it. And a lot of times this is even more important on things like consoles, right? Or non-PC platforms, because it applies to mobile as well. So a couple examples here, there's on the Nintendo Switch, there's a rate limiting. You can only write to the SSD on the Switch a certain amount of times per second, right? So you can't just save the game whenever you want to, or however you want to. You have to fit within that constraint. Platforms like the PS4 have these huge multi-core constraints in them, right? The PS4 CPU is really wide, and each single core is really weak, right? So if you actually want to run a game on the PS4, you have to be multi-core, and you have to be multi-core very efficiently. So iOS, I've done a lot of iOS in my career. There's a lot of nuances there about you can switch between apps, and what happens when your app gets backgrounded, and what happens when the OS sends you warnings that you're using too much memory, and all these things, right? That you have to understand when you're writing iOS games. If you don't understand these things, you're going to run into all kinds of problems, and you're not going to know how to solve them. And obviously the most obvious example of this is cert, right? So every console, you have to go through a process where you submit the game, it gets QA'd by the platform, and they tell you whether it's good enough or not. And they usually have a set of requirements that you have to fulfill. And there's all sorts of weird things that like if you yank the controller cable on the Xbox, it has to, or this is like the old Xbox, but it has to like recover and all these things, So there's all sorts of things like that you have to worry about depending on what platform you're working on. Yeah, on top of that, performance. So performance choices are generally driven by precisely understanding how your code is executed, right? So back to the Katana example, like just using the latest, engine tool or technique is not going to solve your problems. Like using that Katana is not going to mean that I can cut through like 8 straw mats, right? Using ECS in Unity doesn't mean that my code is magically going to be fast, right? You can make horrifically slow ECS code. Like there's nothing stopping you. It's a tool that you have to understand, and you have to use it to solve your problem, and you have to understand why it's solving your problem and how it's solving your problem. And a lot of these things are like, okay, CPU caches, memory layout, memory allocation strategies, all these things. Like, okay, I'm in C#, right? I'm in Unity. Like, I don't have to worry about any of this stuff. Like, that's why I'm in C#. And I would argue that it's actually even more important for you to understand these things when you're using a high-level language than it is when you're using something like C. And the reason is you have very little control, or you have very little direct control over a lot of this, right? Like, do you know how the heap allocation strategy works on iOS in IL to CPP? Like, you kind of need to know that, right? So just to give an example, right? So speaking of the heap, so in Cozy Grove we had this issue where there were a few like low-end devices that would eventually run out of memory after a certain amount of time, right? So the game works fine, and then after 10, 15, 20 minutes, the game crashes because it runs out of memory. So there's a couple of things here. One of them is iOS sends us warnings when we're getting close to the amount of memory that we can use. So in these cases, it was 2 gigabytes of RAM on these devices, and there's an OS and everything running, so you really only get about 1.4 gigabytes to work with. So when you get close to that 1.4 gigabytes, iOS will send you an update or send you a message and say, hey, you're using too much memory. We're going to kill you if you don't freeze some stuff, right? And so like you can respond to those messages, like you can free a bunch of stuff. You try to unload things. And like we initially tried that, and the game kept crashing. So it's like, okay, why is it still crashing? Well, it came down to understanding the platform, right? So on iOS with IL to CPP, the heap size never shrinks. So if you allocate, 2 gigabytes of stuff and then deallocate it, so you only have 20 megabytes in the heap, you're still iOS still thinks you're using 2 gigabytes of RAM, because the managed heap is only using 20 gigabytes for your code, but the managed heap size is still the same because it never shrinks, right? So it's like a lot of this stuff, like we would never have been able to solve this problem if we didn't understand these fundamental facts about the platform. And another quick example, on Windows, we've gotten some bug reports where people have been like, oh, my PC crashed or ran out of battery, and my save file for the game is the right size, but it has zeros for contents. Like there's just nothing in it, right? It's empty. And so you're like, oh, well, BSOD, sorry, dude, like, what are you going to do, right? But if you understand what's happening here, like NTFS, the file system that Windows uses, has this thing called a write cache, right? And the reason it does this is, all right, what the write cache does is when you write to a file, it doesn't actually write to the file to the SSD or to the disk right away. It caches it in memory and writes to it later when it deems that it's safe to flush to disk. And the reason it does this is for mainly performance, but also so that you can save your SSDs have a fixed number of writes in their lifespan, so it sort of saves your SSD if you're writing to the file multiple times. And the way that the NTFS file write cache works is the first thing it does is allocate a file that's the right size with 0 contents, right? So if your file contents are in the cache and you crash, you lose the contents of the file, right? And you might say like, oh, this is just an NTFS issue, whatever. And it's like, no, the reason why it became a problem for us is because we were using things in a way that was exacerbating this fact. Like our save code was not optimized to deal with the fact that there was an NTFS write cache, right? And so like you can solve problems like this that are like these weird, like crazy bugs by understanding what is actually happening, right? And it's not just like these weird one-off things. It's like this iOS example, right? This was like a good chunk of our audience was like experiencing this. So it's not just esoteric stuff. It's like fundamental. Okay, know your platform. Yeah. Okay, the next thing I wanted to say is that everything has pros and cons. And when I say everything, I mean everything, right? So there is no such thing as good code. There's no such thing as bad code, correct, incorrect, proper, or improper code. And there's some pretty cool memes for you. And this is like a really like sort of as like a Zen realization I had in my career. It was like, you know, there's all these things that you learn are like the wrong way to do it, right? And that's useful. It can be useful, but it's not the truth, right? The truth is that there are a certain number of benefits and a certain number of downsides to every single choice you make. Yes, so all code is bad code in some contexts, and all code is good code in some contexts. So it all really comes down to the constraints of the problem and the environment in which you're solving the problem, right? What factors you're optimizing for. So okay, let's make this concrete. This is a little high-level hand wavy. Let's talk about dry. So dry is this concept you learned in school. It's in you know, a bunch of books. It's in like, you know, this one and then this one and like all these things that you read about, like, you know, these are the proper way to do things, right? So don't repeat yourself. Repeating yourself is bad. And it's like, okay, well, let's dissect it, right? Like, why is don't repeat yourself a thing that people talk about? So just real quick, if you're not familiar, this is sort of a contrived example on the left here, but you have two functions, A and B. A prints A 10 times, B prints B 6 times. And you look at these with your little refactoring hat on and you go, okay, they're doing the same thing. The only thing that's different between them is what it's printing and how many times it's printing it. So let me abstract that to a function and then parameterize it based on those two fields, those two factors, right? So what am I printing and how many times am I printing it? And so now you have this, you know, one function C that is used by the other two, and you're happy because if you want to change how you print something, you only have to do it in one place, right? So yeah, so pros. Widespread changes in one place. So if you're using this 100 different places and you want to change how debug the log works, you only have to change it in one place, right? So it's sort of this force multiplier for engineering, which is really nice. Right, and that's the big touted example of like why you should generally do this. It's also less code. Amusingly, the example on the left here is actually more code, but in real world contexts, it's generally less code. Anything that's more than, you know, this contrived example, and less code means there's less chances for bugs, right? It's just there's tons of studies that show that the more code you have, the more vectors for bugs there are. So that's a pretty objective measurement, right? The thing that people don't talk about though is the cons of this, right? So like, this is not always a good idea, and why? So some of the downsides here is that you're adding more indirection, right? You're not just doing the thing that, like, A is not just doing the thing that it was meant to do right now. It's like calling this function with some parameters that is doing the thing, right? So it's a level of indirection. And this is obviously a super contrived example, so it's kind of trivial to look at and be like, oh yeah, I know what's happening. But you can imagine this, you know, times 10, right? If there's 10 levels of indirection here, like it makes it way more difficult to understand what's happening. It's way more difficult to reason about what's happening, to debug what's happening. It's just way more complicated, right? And it's also coupling these two pieces of code together, right? So A and B here are doing pretty much the same thing, but you could imagine A is in some some weird part of the UI code, and B is maybe in some part of the gameplay code, and they just happen to do vaguely the same thing. And so some smart engineer comes along and factors it out. And now suddenly, like, you change a piece of the UI and the game breaks, or you vice versa, you change a piece of the game and the UI breaks, right? It's like these things are coupled together because they're using the same piece of code. It makes the code harder to change, right? You can't change B without also changing A, right? The way that you generally do this is you go into C and you're like, okay, well, maybe I want to, instead of B debug.logging, I want to debug.log warning or debug.log error. So let me add a parameter to C to say, like, what log level warning should it be, right? And then you start, parameterizing these small differences between all of the implementations that you have in the code, right? So C ends up usually being like, in this example, it's only 2 parameters. Usually it's like 8, 10, 15, 20 parameters on some really complex things. And weirdly, this is actually harder to test, right? So a lot of people will say, like, okay, dry is great because you can refactor stuff out to a function and then you can run unit tests on C, right? Okay, great. But if you think about it in the context of adding complexity and adding additional parameters to C to support these little nuanced changes in behavior, it's actually making the problem of testing this code way more difficult, right? So as an example, right? So if C is like maybe 5 Booleans, right? Maybe there's 5 different Booleans for how C should work, and it's called in 6 different places, and they're all using different versions of true and false for each one. If you're doing like unit testing and you want to unit test this, you're talking about unit testing, 5, 2 to the 5th possible, code paths, right? Because there's 5 Booleans, and so it's like, okay, that's a lot. And if you're trying to be, really rigorous about code testing and getting 100% code coverage and all this stuff, then you're making your life miserable. Versus like the 6 places where you're calling this from, like that's 6 different cases you have to test, not 2 to the 5th, right? It's also way more difficult to optimize this stuff. It's just indirection adds a lot. It hides a lot of complexity. It makes it really difficult to tune things very tightly to the parameters in which they need to work. So it's just way harder to optimize code that's written this way. Now, all this is to be said, I am not against dry. I am not saying copy paste for everything. I'm just saying there are pros and cons to everything, right? And we just never talk about the cons of stuff like this because we always just assume, oh, dry is good. Don't repeat yourself. Okay, the other example is more in line with the tweet that I put at the beginning of the slides. It's about hard coding. So generally, we sort of think of hard coding as a bad thing, right? And that's probably right, but probably wrong in some other ways. So why is hard coding generally considered a bad idea, right? A big reason is it doesn't scale. Like, you can't take a hard-coded system and hard-coded thing and turn it into a system of things, right? It's also difficult for people who aren't engineers to tune stuff like that. Like, if you're hard coding all the values for something, it's difficult for a designer to go in and change things. But there's a lot of pros to it, right? So hard coding stuff, like, it's super easy to reason about because it's just there, right? Like, there's no going to a config file, reading a value. There's no abstract system. We're not creating like, all these things to try to do what we want to do. We're just doing what we want to do. Right? It's easy to inspect it. It's easy to modify it, debug it, tune it. It's easier to optimize it because you know exactly what's happening and exactly what needs to happen. You're less likely to need to optimize it because you're using less levels of indirection and less, you're tuning your solution more tightly to the problem you're trying to solve. And I think most importantly out of all of this, it's easier to replace with a different approach later, right? So it's not like this is going to last forever, right? And it's easier to replace something like this than it is to replace something that's been abstracted. So some more benefits here. There's less dependencies, so you're not working in a system where you have an abstracted solution and it's being used in 6 different places. So they're all kind of vaguely tied together. This is it's a piece of code that runs that is available online. It's the code that runs the player controls for Celeste, right? Which are this heralded as like the best platforming controls maybe ever, right? So you look at this code and you're like, oh my God, it's 54,000 or 5,400 lines long. It's got hundreds of functions, hundreds of variables, hundreds of magic number constants. This is the only way I could fit part of it. This is only the variables and the numeric constants of the file in this one screenshot here. You might look at that and be like, oh my God, that's terrible, right? But in reality, like, I mean, this game was made by 2 people, and there was one programmer, Matt, as far as I know, and you know, this was the best solution for them, right? So from Matt's perspective, this is code that, you know, as the designer, he's also tweaking these numbers and making all these changes, and he wants to have something that's easy to debug. And he wants to have something that has precise control over these nuanced behaviors, right? So it's not like you're so you don't want something that has a bunch of like indirection in it, right? Because then you're thinking like, okay, well, you know, there's this jump system that interacts with this, you know, coyote time system, and then I have to sequence these things together to make sure that this happens before this, but then maybe in this one case I want this to talk to this and parameterize this, and it's like, okay, instead of trying to abstract out all of that and work on the abstractions and get the right abstraction for this, he just writes the code that does it, right? And for him, that's much better because he can go in and tune these things and tweak them extremely precisely to get the right game feel. And that's not something that you can do as easily, for sure, with something that's way more systemic, right? Way more abstracted. So speaking of abstraction, my next point here is that abstraction is really easy to get wrong, and it's extremely difficult to get right. So abstraction is something that we all like. I mean, when it's good, it feels like you have superpowers, right? Like if you go on the Python subreddit, it's all these people talking about, oh, you know, I re-encoded these 18 video files at work into 35 formats and 17 resolutions with like 5 lines of code, and then I'm like the hero, right? And that's because like they're using abstraction that's pretty good, right? It can do what they want to do with very minimal input. So you know, there's just the XKCD about this. Incidentally, much of Python's magic is actually just really good C libraries with wrappers around them, but I'll give Python the credit there. So okay, abstraction is good. Abstraction is also not a silver bullet though, right? So abstraction locks you into the specifics of an implementation. What I mean by this is you are, by abstracting something, you are fundamentally looking at your solution and saying, my solution is so good and so perfect that I'm going to abstract out the structure of that solution and use that structure in multiple places, right? I'm so confident in that solution that I don't need to have it in one place. I don't need to modify it later, right? And again, adding indirection makes the code more complex, makes it harder to reason about how to debug, optimize, change, replace, all because you're pulling out the structure and putting it somewhere else, right? You're only leaving the details or the parameters of that structure. So you know, abstracting generic system is significantly harder to optimize. So optimization is often about reducing flexibility in code. So cutting corners, like constraining your problem domains very tightly to the domain that you're working in, or exploiting details of that domain to achieve what you want to achieve more easily or more efficiently, right? And you can't do that when you've abstracted away all the details, right? You just can't. Or you can, but it's, you know, significantly harder, right? And just a quick thing about inheritance here, since that's a general way that people add abstraction, or a method in which people often add abstraction. So inheritance is is so overused. There's no taxonomy in coding, right? There's no, a car and a plane are both vehicles, and so they have, a car class inherits from an abstract vehicle class and all this stuff. Like, no, forget that taxonomy stuff. Inheritance is only about code reuse, right? It's mechanically only about code reuse, and it's about code reuse through tight coupling, right? So you're saying like the plane and the car have some, fundamental things about them that are immutable, that are shared between them, and that we'll put that in the vehicle class, right? That's the only thing inheritance solves. So abstraction is really difficult to do well, right? It's just so difficult to get an abstracted solution, a generic solution that is actually good. And what I mean by actually good is like it actually solves the problem you want to actually solve in a way that is more easy and more efficient than straight line code. I like to think about this as a minimum bound of 3x. So it takes at least 3 times longer to do this, and it generally takes closer to 10x longer to write abstracted generic code than it does to write straight line hard coded, just write the stuff, right? And it's also extremely easy to abstract the wrong thing, or abstract the wrong thing or the right thing in a wrong way, which is a really subtle thing to notice. So I'm not going to go too deep into this because I think that that Casey in this talk does an exceptional job of outlining everything in a way that's way better than I will ever do. So I will just say, you need to go watch Casey's talk from 2004 on designing and evaluating reusable components. So Casey used to work at Rad Game Tools, which makes a lot of middleware for games, and so they were thinking about this stuff a lot. So go watch this talk. Okay, so back to the tweet. So the follow-up things here I was talking about are things that we just went over. So let's see. Overly obsessing about reuse causes nasty, obtuse, costly iteration pitfalls. This bubbles up to other disciplines, especially design, in the forms of, well, it's a 4-hour task, but this is a very minor change that becomes a 4-day task. So yeah, so what I'm getting at here is that a lot of these changes and a lot of these abstractions and all of these choices manifest in your team in other ways, right? So you're shaping the way that design thinks about what they're capable of doing in the game because of implementation details. And ultimately, like, this is like a tech debt thing, right? So you make an abstraction and you have to change the abstraction to meet a new requirement, and then you keep changing it, and then eventually you have this huge monster, and then you have to go back and redo it all, like refactor it or rewrite it or whatever. And you're just like creating this monster, right? So yeah, so it's creating team friction, right? It's you're asked to implement a feature, right? Design asks you for some small change that has a disproportionately large cost, right? That is a big symptom of these sorts of engineering approaches, where you abstract everything into generic code, generic systems, whatever. And more often than not, these happen with cases where we're trying to make an exception to a general rule. Right. So an example here I have is, say you're working on StarCraft 2, which is this RTS, and in StarCraft 2, there's a map, and the map has terrain, and there's generally cliffs, and units have to walk around cliffs. They can't go up and down cliffs. And then pretend one day that your designer comes to you and says, Dustin Browder says, "Hey man, I want to add a Reaper," and then what the Reaper does, if you're not familiar, is it's exactly the same as another unit, but it can jump up and down cliffs. So if you've abstracted the unit in this game to be a thing that moves within the context of what's walkable or what doesn't have cliffs, right? You've abstracted it up to that. Then you sort of have to go, okay, well, if I add a Reaper, then I have to change my abstraction to parameterize whether I can touch cliffs or go up and down cliffs or not. So you're bubbling up the Reaper's behavior into this abstraction layer, and then that has complexity implications to the rest of the game, because everything else has to say, like, no, I don't go up cliffs, or no, I just walk within normal areas. So this is perceived costs versus actual costs diverging, and this is a symptom of over abstracting. It's a symptom of incorrect abstractions, which I think is the more insidious one. Incorrect abstractions are really difficult to identify and to fix because the code mechanically looks good, but it's difficult to change, right? It's also just a symptom of overgeneralizing things and over-engineering in general. So when a proposed change doesn't immediately fit the abstraction, we need to change the abstraction, which is expensive. So it's the thing I just talked about where, we're adding a Reaper, so we have to change how the unit abstraction in StarCraft works to be able to parameterize whether you can go up this kind of terrain, right? So this is the biggest point I want to make in this entire talk, is to solve the problem you actually have, not the problem that you think you have. And I think this applies in so many ways, right? So you can think about it in performance, right? You think a piece of code is like the hot area of code. And this part of code needs to be really fast because we're going to do a lot of stuff here, and it's going to be really heavy duty. But it's almost never, you're almost never right? You always want to go optimize things based on profiles. Right? You have to be an engineer. You have to look at things objectively and evaluate them objectively, not sort of guess or go by gut feeling that like, oh, this is a really important piece of code that has to be fast. It also applies to this abstraction thing that I'm talking about, right? So if you're starting out working on StarCraft, right? You're starting from scratch, StarCraft 2. Here we go, right? You're adding a zealot. Right, so you're thinking, okay, I need to add this abstract concept of a unit because we're going to have a bunch of units later down the road, and I know we're going to have, every month we're going to be adding a new unit to the game, and so I need to, set things up for that. It's like, I understand where that's coming from. That's generally not what you should be doing, though, because that's not the problem you actually have. The problem you actually have is you need a zealot in the game, right? Games change so frequently, schedules. Just designs, everything changes so frequently that you can't presume these things, right? In my StarCraft example, like you add a zealot to the game, and maybe Dustin Browder goes, "Hey man, we just need zealots." Like it's just StarCraft 2 just only has zealots, but it has all these other interesting things. And so then you've created all these abstractions that you're never going to use, right? Because you've abstracted things before you needed to abstract them. You've solved the problem you thought you might have, rather than the problem that you actually have right now. Okay, so in summary here, being an engineer is about being ruthless and ruthlessly objective about evaluating your problems and your solutions. As a software industry, we're horrible at this, right? We're very much driven by like what's the design pattern for it? What's in this thing, or like what's the latest strategy, right? Like when I was first entering the industry, like entity systems were like the hot new thing, right? So everybody's doing entity systems. We're very driven by that sort of trendiness, and that's not engineering. That's just trendiness. Like you have to be objective about evaluating your solutions and why they solve the problem you're trying to solve and how they solve it. Understanding the fundamentals of what's happening in a computer are essential to understanding how your code behaves. Again, you have to understand like what's actually happening in the computer, like what your code is actually doing. Like even if you're using C#, even if you're using high-level stuff, you have to understand what it's doing for you, so that you can understand how to debug it when it goes wrong, because it will go wrong. Optimizing for ease of change is, I think, the most important factor when making games. Like I was saying before, like requirements, designs, platforms, deadlines, schedules, they all change constantly, and you can't make any assumptions about any of them. So the best way that you can write code for games is to write code that's easy to replace, right? Code that's easy to change when you need to change it. And abstractions are inherently resistant to change, right? They're like I was saying before, like you're so confident in your solution that you're abstracting out the structure of that solution into a codified thing, right? Which means that if you need to change that structure, you can't change it easily. So the general guidance, I like to think about some people call it the rule of threes. I like to think of it the rules like rule of 3 to 5s, which is like if you have something, if you have 3 to 5 things that are vaguely, they're pretty similar, and you want to add an abstraction to it, then that's probably a good abstraction. Like 3 to 5 things is a good level to be at. Like if you're working on StarCraft, you have 3 to 5 units. Like okay, then you can start thinking about like okay, what if we abstracted unit class or things like that, right? Yeah, abstractions also locking into a specific implementation. Like I was saying before, you're abstracting the structure out. So yes, again, solve the problem you actually have, not the problem you think you have. Like this is so fundamental, and so we get this so wrong all the time. Like every single like thing I'm talking about is you could look in this context. You could say like, okay, performance, design, all these things are solving problems that you don't actually have. Yeah, and so how do we get better at this? We practice. I'm a big fan of Pico 8 and in old console development, but Pico 8 is way more tractable. And the reason is that you can't like make abstract, crazy, generic things there, right? And so it forces you to think in this other approach, right? Because there's literally a character limit for Pico 8. Like you just run out of source code characters if you do too much. And console development too, old consoles, like the constraints there are so intense. Like you're literally chasing the electron scan line across the CRT, right? That you have to think in the context of like, okay, how do I do a thing with the minimum amount of code I can possibly use, right? What is the minimum viable code to solve a problem? Like Mario doesn't have an entity component system. Like it's just like some numbers and some math, right? So if you start thinking this way, then what you'll end up doing is you'll end up thinking about problems in other contexts like this, and your code will be drastically simpler and drastically easier to modify. So I'm sort of saying all of this coming from learning it from other people, and these are sort of the people to look at for a lot of this. So Mike Dacton, this talk is just, it might as well be the 10 commandments of game programming. Data-oriented design in C++. It's very C++ oriented, but like all of the concepts in this are excellent and applicable everywhere. If you haven't seen it, go watch it. How to program independent games. John Blow did a talk very similar to this about his strategies to do independent games. He talked more about like optimizing for implementation time, right? Because he's making games on his own or in very small teams. And he's generally the designer and the coder, so he can do a lot of stuff like that Matt was doing with Celeste. The other talk by Casey that I mentioned earlier about designing and evaluating reusable components, that's like the resource for thinking about anything related to reusable code. Just go watch that, and then it will like change your mind about how to think about things. And then the 30 million line problem is an interesting talk by Casey. It's a little ranty, but it talks about the things that I was getting at with knowing your platform, right? Knowing how all of these stacks of things work down to the metal in order to actually write things that work. Cool. So we have like 10 minutes left, so I'll open it up to Q&A, and feel free to flame me on Twitter if you disagree with me. Cool.
Hello, I'll go first. I'll flame you on Twitter.
Nice.
So, all right. So how is building your data structures in a way that will preclude, say, caching problems down the line different from building your class structures to preclude problems you think you have? And like one of the things that comes to me is like, okay, we have an inventory system. We're going to have some items that are usable and unusable. And then we decide, okay, and there's some items that are stackable versus unstackable. Do we really want to have 4 different classes for our items? Do we have like different ways for each of them? When do we abstract? Do we do it after the first split or the second one? And how is having like a bunch of functions with a bunch of switch statements different necessarily from having a bunch of different classes themselves?
Sure. Yeah. So that's a great question, and it's not. Unfortunately, a lot of this stuff is, it's not. There's no cut and dry, right? There's no. You should always do this. You should always do that. But the way I think about it is, you know, coming back to what I was saying on Twitter earlier, like in 99 cases out of 100, you shouldn't abstract something like that. And you might think, okay, there's going to be switch statements everywhere. It's going to be a mess, and that's absolutely true. But the alternative is just as messy. It's just split over a million files, right? So you're moving, you're splitting your switch statement cases into different functions in different classes that are overriding some base class or some interface or something like that. So when you go to look at like, oh, how is this, how does this behavior work, right? We have to go look at, okay, well, it's calling it to this abstract function into this class that's used in 18 different places, right? And then we have to go open those 18 different files and look at all the overrides for all of those. And maybe there's multiple layers of inheritance there, right? So I think it's messy in a different way, and I think that's a lot harder to see. It certainly was for me early in my career, right? So, and like the switch statement stuff is like it's messy because it feels like there's no structure, but there is structure, right? And there's a like you can look at that switch statement and know exactly what's going to happen very easily. Yeah, it's unfortunate because there's not like a hard and fast rule. Like I was saying, like 3 to 5, but in reality, it's like you have to look at the situation and make an objective measurement of like, is this going to be more complicated or not?
Awesome. Yeah. Thanks for that.
Thanks for the question. Anybody else? Cool. I think that's it then. We're 6 minutes before the next talk, so thanks for coming. Thanks for listening to me ramble and have mic problems, and have a good FIG, and stay safe. Cool. See you around.